Hello everyone, welcome to our presentation about AdapTutor. This program is talking about an evolving dual-agent framework for synchronized learning support in online learning environments. I am the student Yiyao Zhang, and my supervisor is Dr. Lin Yue, and we work at Adelaide University. The problem is that when facing large-scale education, books are rarely filling. There are millions of learners, but urgent questions go unanswered. The interaction deficiency. Books serve millions, but manually one-to-one tutoring is impossible to scale and could be expensive. There are noise over signals. Discussion forums become unmanageable when urgent queries about deadlines or misconceptions are buried in irrelevant information. And there are critical timing. Timely, personalized feedback is a single vital predictor of learning outcome in digital environments. There are around 19% dropout rate on major MOOC platforms due to frustration and disagreements. There are some existing paradigms, but they are fragmented and static. Prior approach detect or respond, but none could self-evolve over time. There are some paradigm, approach, and critical limitations. First, there are discriminative detections like BERT robota classifiers, but they are detection only. No response is generated, and this is their limited capability. And there's generative LLM and RAGs, GPT-4 with retrieval augmentation, but they are prone to hallucination, no strategic learning from the feedback. They are autonomous agents, but they are tool use and multi-step reasoning. They are static policy, cannot self-evolving without manually re-engineering. The key takeaway insight is that no existing system integrates urgent detection, response generation, and strategic learning together. Then we have AdapTutor, a self-evolving dual-agent framework. It can unify detection, response, and continuous evolution. First, we have student post. This is raw text input from the forums, and then it can be delivered to the urgency classifiers, which includes burst and hierarchical attention. Based on the situation, it should be delivered to template agents and LLM agents. Agents work like a general practitioner, which use reinforcement learning and imitation learning to evolving their pro algorithm. And for the LLM agent, we use genetic algorithm. It will be specialized in the specific problem, and then we will continuously evolution to get the final optimal performance. For the template-based agent, we use reinforcement learning plus limitation learning. Reinforcement learning working alone explore blindly, but imitation learning provides expert-guided foundations. For the agent specification, there are state space. For example, there are rich NLP features, and we use TF-IDF, expert, sentiment, urgency to classify them. Then we have action space. We select from the 15 curate pedagogical template, and we have network architecture using DQN. For the input, we have for 500 layers, and then 200 layers, and then 100 layers, and then go to the outcome. And the learning strategy is that first, we use imitation learning, which is GARL. Learn from expert instructors demonstrate to bootstrap the policy, avoiding the cold start problem of random exploration. And then we use reinforcement learning, refine the policy through interaction, optimization for the pedagogical quality, which includes relevance, helpfulness, and clarity. We can see the combined reward function. The total reward is depend on the reward of pedagogical and the penalty of the clarity of the reward of the final answer. For the LLM-based agents, we use genetic algorithm to optimization, intelligently exploring the hyperparameter set to evolve the specialist agents. First, we use the chromosome algorithm. Each individual represents a complete LLM configuration. We have temperature from 0 to 2. We have max tokens from 16 to 500. We have top P from 0 to 1. The population size is 15. And we have genetic operators. We have tournament selection. We have k equals 3 for the select best parameters. And then we have uniform crossover. T equals 0.8 for the mixed parameters. Then we have Gaussian mutation. T equals 0.1 to the explores new values. For the 3, we have fitness function. Measure responsible quality across a standardized query set. Fitness equals average or quality score. We have relevance, helpfulness, clarity, and engagement. The advantage is that genetic algorithms escape local optima. Research can miss top combinations. For the dataset and experimental setup, we are validated on the Stanford mock post benchmark with 10,000 real forum posts. The dataset species is that the source is Stanford mock post dataset. The volume is 10,000 annotated posts. The class is imbalanced. Nearly only 23% of are urgent. They are realistic distribution, and we stratify the dataset into split. 17% are for training, 15% are for validation, and 15% for test. And we proposing that and text cleaning, HTML removal, contraction expansion, and code block tokenization. We have feature extraction. We have lexical engrams. We have semantic post and semantic sentence bird, programmatic features, sentiment analysis, and question markers. They have temperature features. We have timestamp start, date deadline. We can implementation this, build with robust, modern stack. We use Python 3.9, PyTorch, OpenAI API, GPT-4o, and Sentiment Bird. The hardware is standard GPU and API-based inference. The first result is urgency classifier performance. We have fine-tuned BERT with hierarchical attention achieved 84% accuracy. We can see from the left graph their accuracy percentage and F1 score in percentage. We can see in blue that our model performed the best. On the right table, we can see the model accuracy, precision, recall, and F1 score. Our model performed best on the general situation, and the BERT only and LIWC plus IDA boost perform less than this one. We have key findings. It is high sensitivity, which means it ensures urgent student posts are rarely missed by the system. We have hierarchical attention. We have successfully captured high-level and global post-level urgency signals. Then we have result 2, template agent evolution. AdapTutor with reinforcement learning and imitation learning rises from 0.3 to 0.4 quality over 13 evolution cycles. On the left, we can see the graph. There are title quality evolution over cycles, and there are x-axis and y-axis with evolution steps and quality scores. We can see AdapTutor has a higher score compared to the other one, which includes static keyword, static patterns, and reinforcement learning only. And we can see from the right table, we have method, mean Q value, peak Q value, and times. AdapTutor with reinforcement learning and imitation learning perform the best, but reinforcement learning and static pattern perform worse. The response time is pretty small, and the key insight is that imitation learning (RL) provide a robust starting point, while reinforcement learning can continuously fine-tune the train and finally gradually outperform static baselines. Results show that LLM agent evolution. AdapTutor genetic algorithm reached a peak quality of 0.565, far above all baselines. On the left graph, you can see that there are generation steps and quality score, and the AdapTutor genetic algorithm has performed the best, compared with static fine-tune, theoretical retrain, and grid search. On the right table, you can see method, mean Q value, peak Q value, and times. AdapTutor with genetic algorithm performed the best, compared with periodical retraining and grid search. The performance gain is at 85% plus improvement in the mean quality over grid search baseline. The key insight is the genetic algorithm successfully navigate in the complex hyperparameter space and guide the tuning procedures. Then we have ablation study. We have component contribution analysis. Reinforcement learning and imitation learning are complementary. Removing either will degrade the performance. For the template species agent, AdapTutor with reinforcement learning and imitation learning has the highest score, whether without reinforcement learning or without imitation learning, both degrade the performance. The one with static pattern matching has the worst performance. The key takeaway is that synergy is imitation learning provides a pedagogical sound starting point, while reinforcement learning refines it. neither work as well alone. And for the LLM agents, we have AdapTutor with genetic algorithm perform the best compared with the grid search. The takeaway is that optimization power is the thing. Genetic algorithm outperform the static baseline by almost 18%, proving that intelligent exploration is a crucial point for the dimension nor LLM parameter space to be optimized. Discussion, implication, and limitations. AdapTutor skills student support will acknowledge real-world constraints. The first is practical impact. Reduce instructor workload. Routine queries are handled automatically, freeing instructor to focus on high-value mentoring and complex pedagogies. There are immediate student support. This provides consistent, instant feedback, which is directly linked to the increased engagement and reduced dropout rates. And there are economical practicality. Dual agent assign is cost efficient, and it's a cheap template agent for volumes, and expensive LLM only for complex cases. And there are limitations. Dataset generalizability. It is evaluated on a single English language dataset from technical computer science courses. Its performance in humanity is untested. It is template rigidity. The template agent relies on the pedagogical library. It's limiting the novelty and flexibility of its response. It has proxy metrics. Automatic quality score are robust proxy, but for the short term, but in the long term, this measure is not so accurate. Future direction and conclusion. AdapTutor established a replicable foundation for adaptive education in AI, and future direction includes cross-domain generalization. It is validated across humanity and social science to ensure the framework isn't limited to technical subjects, and it should be advanced in the personalization, extend evolution mechanism to adapt to the response based on the individual student learning history. It should have in longitudinal study. It will conduct individual studies in the live MOOC form to measure long-term impacts on retention and learning outcomes. It shall have human-AI collaborations, positioning agents as an intelligent assistant for instructors, fostering a collaboration support ecosystem. The conclusion is that AdapTutor demonstrates that self-evolving dual-agent framework can successfully unify urgent detection, intelligent response generation, and continuous adaptations. By bridging the gap between autonomous detection and intelligent resolution, it offers a scalable solution for the interaction deficiency in the large-scale online learning platforms. Summary of key results. There are three strong results validate AdapTutor's end-to-end effectiveness. There are 84% accuracy. Urgency classifier outperformed bird-only baseline by 3% with high sensitivity and specificity. 27% quality gain. Template-based agent reinforcement learning plus imitation learning achieve peak quality of 0.46, significantly improving overall static pattern matching. And there are 85% accuracy improvement in the genetic algorithm. And thank you for your attention. If you have any question, you are welcome to connect me. Well, this is a AdapTutor, a dual agent evolving platform. If you have any question about dataset, methodology, code implementation, and discussion, please feel free to contact me. And I have listed my contact details in the bottom. My name is Yao Zhang, and I work at Adelaide University. My email address is yaozhang@student.adelaide.edu.au. Thank you.